Let's see how generative AI works.
So let's say we have an input sequence, and based on that sequence, we want to generate follow-on sentences. So here's our input sequence, and based on this prompt, we want to generate follow-on sentences. So first, our input will be tokenized, which means that our sentence will be split into words, which are called tokens. Next, each of the tokens will be assigned a numerical ID. Think of these numerical IDs as distinct position of those words in a very large dictionary. And we need to do this because the machine only understands numbers. Now our input IDs will be transformed into a high dimensional feature vector. This is a high dimensional feature vector containing many, many numbers, which collectively are capturing various features of a word, which help us in understanding the contextual meaning of each and every word and their association with every other word. And these feature vectors are referred to as embedding vectors. Next, these embedding vectors are fed into a model that encapsulates the contextual similarity of words and produces an enhanced representation of our input sequence. So, for example, now our model can tell that the bank here refers to water and the bank here refers to money. This augmented version of the input is now fed into a model head, which will perform the desired task, in this case, next sentence generation. So based on a deep understanding of the input sequence and its prior training on billions of words, our model can now generate newer sentences based on the input sequence we passed. Okay, let's put all this together. So we have an input sequence. We pass the input sequence into our model. It gets converted into tokens. Tokens get converted into input IDs, and the input IDs are thereafter transformed into these high dimensional feature vectors. These feature vectors capture many different features of a word, which not only help us in getting a deep understanding of the contextual meaning of the word, but also its association with all other words in the input sequence. And these feature vectors are referred to as embedding vectors. And these embedding vectors are then passed into an algorithm that enhance the context of each and every single word, which is then finally fed into a model which is tuned to perform the desired task. So the real magic here is happening here. So what exactly are these feature vectors and how do they help us in understanding the association between two different words? So to get an intuition of this, let's assume we have three different words, king, queen, and layman, and our algorithm is able to capture five different word features. And we'll score a one wherever it is positive, except for gender, where we are encoding one for male and zero for female. So these are the scores that our algorithm passes for these three different words. So wherever it is positive, it gives a one. Wherever it is negative, it gives a zero. Except of course for the gender. And now our next task is to compute the similarity among these three different words. So what we're going to do is, or rather, what the algorithm will do is, it will just do a dot multiplication between the scores for each and every feature between those two words. So this is what we get. King and queen is 1:1, 1, 1:1, 1, 1:0, 0, and so on. So cumulatively, what we get is a score of 4 for king and queen, and 1 for king and queen, and layman as 0. So the higher the score, it denotes a higher similarity between those two words, higher association between those two words. And if we really closely look at this, there's nothing but a dot multiplication. So let's get a graphical understanding of this to make it visually more intuitive. Okay, so here I've defined three vectors, v1, v2, v3. Each is a three-dimensional vector. And there is a short code here which is going to compute the dot product of each of the vector with every other vector. And it plots it out in a 3D space. So as we previously saw, that higher the dot product, closer are the vectors in a high dimensional space. So here the dot product of v1 and v2 is the highest, which is 20, and v1 and v2 are denoted by red and blue. So as we can see in a three-dimensional space, they are very close to each other and the other vectors are quite far. If you were to just change this value, the dot product will change and so will their projections. So now we see that the dot product of vectors 2 and 3 are the closest, which is blue and green. And we can see that in a three-dimensional space, these vectors come much closer to each other. So this is how mathematically we can compute the association of different vectors, which in turn are defining the whole feature attributes of a word in a high dimensional space. So this is a three-dimensional plot to give an intuition, but this is what it's going to look like in a very high dimensional space. So let's take a word here like bank, which we previously took in our example. And now it's showing all the words in a very high dimensional space, which are closely associated with bank in different contexts. And here we see 10 words which are most commonly associated with banks here. So you can see bank, monetary, banking, IMF, fund, currency, so on, which is all in the financial domain. But if you look closer here, you can even find, let me see if I can zoom this in. So if you see closely, you can even see Gaza, you can see Swiss, you can see Canal, and you can see river as well. So here in a very high dimensional space, the vector dot products are computed, and there are different weights which are assigned through a neural network. And that's how the associations are formed in a large language model. So here we've taken an example of one such algorithm which is converting word into vectors. It has been trained on different data sets. So here, as you can see, like one of the data sets is about 1 million word vectors, which is trained on Wikipedia data. There's yet another which is pre-trained vectors, which are on 2 billion tweets, and likewise some 400,000 records on yet another data set here. So all of these are vectors, and if we want to see similar words, we just run something like this, and it's going to show us that with a very high probability, and it's assigning a probability score, which are the words which are most closely associated with T. And similarly, we can also see the similarity between two different words. Or here, we are talking about distance. So if tea and coffee are close to each other, their distances should be small. And here it's 0.43, as against, let's say, the distance between T and P, which may sound similar, but in the vector space, the distance is almost about 60 or 70% more than the distance between tea and coffee, which are contextually more closely associated. So this is how mathematically in a high dimensional vector space, the associations between different words are learned by the machine, and that's how the machine starts understanding natural language like a human and is able to establish contact and thereafter perform various tasks which we ask of it, which could be text summarization or culling out the sentiment of a particular paragraph that we've given, or we can give an input as a text and we want it to generate the follow-on text, or we can give an image and we want it to be captioned by a text, or vice versa. So I hope you found this useful. And our mission, or rather our effort, is to ensure that we make artificial intelligence accessible to everybody through bite-sized videos in a language which is easy to understand, jargon-free and intuitive. And if you'd like to reach out to us, our email is below. Please do reach out to us. There are various channels through which you can link with us as well. And I'll see you again.